Okay, so in this video, we're going to look at an introduction to working with polar coordinates. Now, in this transformation between rectangular coordinate systems and polar coordinate systems, we have this general relationship that x is equal to r times cosine theta, and y is equal to r times sine theta. And that is one relationship that converts our xy coordinates that are in rectangular form to polar coordinates that will be in terms of r and theta. So again, think of x and y. X is the horizontal distance that you've moved from the origin, and y is the vertical distance you've moved from the origin. R and theta are essentially saying, I'm moving this far away from the origin in r, and then I'm moving at an angle relative to the x-axis, and that is my second coordinate. So a magnitude and distance instead of magnitude in one direction and magnitude in a second direction. Now, it is also sometimes useful to think about this in terms of the triangle. So x was our coordinate in the x direction. R was the hypotenuse of our right triangle. That gives us adjacent over hypotenuse. That gives us cosine. Similarly, these are derived from our sine definition. The opposite over the hypotenuse gives us the sine. And so we've simply rearranged these for x and y. Now, if we want to relate x and y to each other in another way, maybe we have slightly different pieces of information. We can also use this relationship of the circle, x squared plus y squared is r squared, and that the angle, tangent theta, is equal to y over x. So again, think about this as opposite over adjacent. That's how we get that theta. You can also think of this in terms of r equals the square root of x squared plus y squared, again, derived from the Pythagorean theorem, or inverse tangent of y over x is equal to theta. Now, one thing to keep in mind for the inverse function, it's only going to give you angles in the first and fourth quadrants. If your angle is actually in the second or third quadrants, because that's where your x and the y coordinates are, you will have to add pi to your result from doing this calculation. Now, just to, again, remind ourselves or to indicate how these things work. So r is the distance from the center. So each of these concentric circles, you can think of them, this is 1 unit away, 2 units away, and so forth. So these regularly spaced units going away, this is in fact 2 units and 4 units and so forth, but going away in the radial direction. And then in the theta direction, theta is going to be these lines going through the origin. So when the angle of tangent is 0, then tangent of theta is 0, and you get the slope of this line is 0. And when y and x are the same value, then you actually get inverse tangent of 1, which is pi over 4. It's going to be this line at the 45-degree angle. If it's lower, then you get one of these. If it's higher, you get one of these. And so these lines are going to break up our region. I've actually done them at multiples of pi over 12 because pi over 3 and pi over 4 and pi over 6 are all going to be multiples of pi over 12. So the 1 pi over 12 will not be a standard angle, but then 2 pi over 12 will be pi over 6, 3 pi over 12 will be pi over 4, 4 pi over 12 will be pi over 3, and then those are all standard angles, and then 5 pi over 12 will just divide that last section into a nice even group until we get to 6 pi over 12, which is pi over 2. So each one of these lines represents an angle of pi over 12 so that we can represent all of our standard angles from our triangle. Not only the axes, but also the 30, 60, and 45-degree angles. Now, if I want to plot a point in polar coordinates, I need to, the first coordinate is r, the second coordinate is theta. I go out 4 units, and then I find the line that matches up with my angle, so pi over 3. So in this example, I'm going out 4 units. Notice this R circle goes through X and Y equals 4. And then my pi over 3 line, remember, that's 4 pi over 12. So that is that position on the coordinate plane. That is my 4 comma pi over 3. Now, if I wanted to do 6 and 11 pi over 4, since the angle is larger than 2 pi, we actually go all the way around the circle. And if I subtract 2 pi off from this, that is equivalent to 3 pi over 4. And so I will go out to a circle, an imaginary circle on here of radius 6. And then my 3 pi over 4 is this angle in the second quadrant, and where that circle of radius 6 intersects with that angle of 11 pi over 4 or positive 3 pi over 4, then I will put my dot there. Now, this brings up the point that they're in polar coordinates, the points in the plane are not unique combinations of coordinates. Negative angles will just mean I'm going around in this opposite direction. So I can also get to this point from negative 5 pi over 4. And it also means, in fact, that if my angle switches by pi, I can get back to this position by making my radius negative. So rather than using, I can use this angle negative pi over 4 or 7 pi over 4, however you want to represent that. But then a positive angle, positive radius would go outward from the center in that coordinate direction into that fourth quadrant. But if I had a negative radius value, stay on that same line, but go in the opposite direction, that will still get me to this point in the plane. So even though our default representation of radii is positive, to make polar equations continuous, we will allow angle or radius values to be negative. And so that does also give us an extra set of points where the radius value is negative and the angle is on the opposite side of the graph. And that's how we get back to where we're supposed to be. So these representations are not unique representations, and that is something we have to keep in mind when we do this work. Unlike rectangular coordinates, where every point in the plane has a unique and distinct coordinate pair. Now let's do one more. Again, we're starting with a negative radius and the angle pi over 6. So initially, the angle pi over 6 goes out in this direction. But since our radius is negative, we will actually go, instead of outward from the origin in this direction, we will go backward in the opposite direction until we intersect with that circle of radius 8. And so we can see that that point is actually in that third quadrant. It's now equivalent to the point with a positive radius of 8, but an angle of 5 pi over 6. So this is our 5 pi over 6, positive 8, or angle pi over 6 and a radius of negative 8. They're the same point. Now, another task that we might want to do, not just plotting points, but we might need to convert points back into rectangular coordinates, or we might have a point in rectangular coordinates that we want to convert back into polar coordinates. Now, which of these pairs of formulas that we talked about earlier, those combinations of different functions, are going to depend on which kind of information we have. So if I'm trying to convert coordinate points back into X and Y, then these are the two formulas that I'm going to need. So in our example, in the point 4 pi over 6, R is 4 and theta is pi over 3. And so I'm going to plug that into my R cosine theta formula to get X. And if I plug that information into my R sine theta formula, then this is pi over 3 times 4 is going to be pi 2 pi over 3 is going to give me square root of 3 over 2, and times 4 is going to give me 2 square root of 3. And so my coordinate point in rectangular form will look like this. Similarly, if I have 6 and 11 pi over 4, I plug in to this equation, and 11 pi over 4 is going to give me negative 1 over the square root of 2, or square root of 2 over 2 times 6. That's going to reduce to negative 6 times the square root of 2. And then similarly over here, although it will be positive in that second quadrant, and so I will get this point. And then likewise, we can plug in the same information. And again, here the radius, that negative sign will carry through. And as we saw with our graph, we are in the third quadrant for this point. Now, if we're going from rectangular coordinates to r and theta, it's actually more useful when we have coordinate points to use the other set of equations that relates. So we have the r squared, x squared plus y squared equals r squared, and the inverse tangent function. So here, if I'm going from the point 1, 1, and I want to put that into polar coordinates, then I use x squared plus y squared. That's going to give me 1 squared plus 1 squared, that's 2. And then so my radius is then the square root of that, which is square root of 2. And then my inverse tangent, y over x, 1 over 1. What angle of theta gives me tangent equals 1? Well, it's the pi over 4. And so our theta form, square root of 2, pi over 2. And then for some of these other ones, you're not going to get nice angles. The inverse tangent of negative 2/3, that's not a standard angle. So you convert to radians by default. And so if we walk through just this one additional example, 3 squared plus negative 2 squared, that's our x squared plus y squared. 9 plus 4 is 13, so r is the square root of 13. But then this inverse tangent, not a standard angle, and so we convert that to radians. We can use our calculator for that. But our point, 3, negative 2, if this is in the fourth quadrant, then we can use this value, or we can add 2 pi to it to make it on the standard 0 to 2 pi range to get this. If we're in, let's say, the third quadrant, inverse tangent is not going to give us that value. And so we're going to need to add pi in order to get into that third quadrant. So you do have to pay attention when you're going in this direction to what quadrant you're supposed to be in, because you can't just use this function blindly. That will only work in the first and fourth quadrants. But if you're in the second or third quadrants, you will need to add pi in order to get the angle right, or flip the sign of your radius if you would prefer. Now, when you convert equations, it's actually going to be easier in a lot of cases to either use all of the formulas that we were looking at simultaneously, or to actually use them in the reverse relationship. So the coordinates that we use to convert from polar to rectangular in coordinate form are going to not necessarily be the ones that we want to use to convert equations from polar to rectangular form, and so vice versa. So you kind of want to look at your function and then use all of them that are available in order to make your arithmetic as simple as possible. You will need to get a simplified version of your equation. And if you use the wrong version, like you use x as r cosine theta, and then you stick that into an equation where you have to square it, you are going to have to simplify, pull out your r squared, and then simplify cosine squared plus sine squared. You can't leave it in this big, ugly, nasty mess. So choosing the right formula for the conversions will be important. So here's an example of an equation. It's a circle in rectangular form. If I want to convert this to polar form, then I should multiply my x minus 5 out before I do my conversions. And when I do that, I end up with this expression. So I put everything on one side of the equation just to make things easier. I'm getting x squared minus 10x plus 25, and then the minus 9 comes over and gives me this 16. And then I can use my x squared plus y squared is equal to r squared. Again, not the x is y, r cosine theta version. Don't do that. Just x squared plus y squared, that's r squared. And then here I can use the r cosine theta because I'm not squaring it, or I'm not going to have to simplify it. There's nothing I can do there. And then the 16 doesn't convert. Now, in order to graph this in our calculators, we would have to put this into polar form, unless you're using an online function like Desmos or something, which can often do these in implicit form. But for this purpose right now, this was not like the best polar graph. We're just going to leave it in this form. You do want to make sure that when you're converting from rectangular to polar, that your final polar equation has only r and theta terms and has no x or y terms. Similarly, if we start out with an equation in polar coordinates and we want to convert it to rectangular coordinates, we do need to make sure that we are eliminating any r's and thetas and only are left with x and y. Now, if we go in the other direction and we start with something like r is 3 cosine theta, then we don't want to just use our theta equals inverse tangent of y over x, because leaving cosine of inverse tangent is a mess. We want a algebraic expression, not a trig function with an embedded inverse trig function in it. So we're going to actually do a little trick that works very frequently, especially in textbook problems, is we're going to multiply both sides of this equation by r. And when we do that, the one side of the equation that was r is going to become r squared. And on the other side of the equation, we're going to get r cosine theta. And this makes our substitutions much easier. R squared is x squared plus y squared, and r cosine theta is just x. And so now we're in polar form. We're in rectangular coordinate form. If we wanted to try to solve for y or put this in standard form of the circle, we would have to move the 3x over and complete the square. But if you get this far, you are in rectangular coordinate form, and at least I would be happy with that. Now, if I want to graph a polar equation by hand in polar form, not converting it back to rectangular, then I need to choose values of theta and use that to calculate the size of the radius and then plot consecutive points. Now, as we saw in the past, typically polar graphing paper has radial lines for theta and multiples of pi over 12. And again, that's because they pass through all the standard angles, pi over 3, pi over 6, pi over 4, pi over 2, all of those. Now, we can go down to smaller angles. So if we have functions like cosine of 2 theta, we can go down a little bit further because we're going to multiply by 2 before we have to plug in any values. And so those will be easy to calculate with standard angles once we multiply the angle by 2. And same thing if you're doing cosine of 4 theta, you're going to need more points in order to get the details of the graph. But you can go down to smaller angle values because you're going to multiply by 4 before you plug things in. So for something like this, if I plugged in pi over 24 times 4 would get me pi over 6. So I would be able to evaluate the cosine at a standard angle, even though the angle that I'm going to plot the point at was only halfway between 0 and pi over 12. So it helps to think about this, because again, if you're plotting cosine 2 theta or cosine 4 theta or even cosine 3 theta, you do have to think about to make sure that you're plotting enough points, because the graphs are going to whip around and do all these pedals and crazy things much more quickly. And if you jump over too many values, you're going to end up not getting the graph correct because you're going to be skipping all of the details. So let's look at a sequence of plotting a graph 2 minus cosine theta on a plotter. Now we're going to start by plotting theta equals 0. We plug that in. Cosine of 0 is 1, so 2 minus 1. We're going to start at 1 when theta is 0. And then we're going to start out with theta equals pi over 12. And then connect the dots together. And again, pi over 12 is going to be, probably you'll have to evaluate it as a decimal in order to get the value to figure out like how far away from the radius am I. But when you get to pi over 6, then cosine of pi over 6 is a standard angle. You do the subtraction, you can calculate the value. And then again, we start connecting the dots, we plot points, and we end up drawing out our graph as we connect the dots. So with each subsequent angle, we get further and further and further to our complete graph. Now, another strategy for plotting these functions is that you can plot them in rectangular coordinates. So think of y as your r and x as your theta. And then from this rectangular graph, you can collect the values for your function. Now, though this is just a strategy that you can use, some people really like this. Some people, I think, find it difficult to switch between the meaning of the point on this graph and the meaning of the point on the polar graph. But that is another strategy that you can use, especially since when you're plotting, you're estimating the value of the radius. Sometimes the values of the radii are very weird values and not like nice whole numbers. And so estimations are what you're going to have to do anyway. Rather than put things into the calculator, you can use this as a way of, again, plotting it on a standard graph. This is not a polar coordinate graph, but then translating these y values into radius values for your polar graph.